actually. Okay. Today we gather to discuss and with topic the material limits of energy storage, supply chain, chemistry, sustainability, and the way forward. I think it is a good, good topics for us. So, energy storage has indeed become the new norm as we scale up the renewable energy source and accelerate the shift from fossil fuel to electrification. Nowadays, become new norm. We can see in every place, especially in China. We are we are witnessing a global surge in electrical vehicle adoption and grid-scale storage solution. At the core of this revolution lies fundamental understanding and rechargeable battery and material that comprise them. However, as we push forward, we are increasingly confronted by critical bottleneck, the material themselves. So almost the problem is the material, right? So where do these critical mineral come from, and how are they processed? What the geopolitical environmental implication of our rapidly growing demand? And most importantly, how do we build sustainable pathway forward does not compromise our future while solving our present challenge, right? Okay. There, these are not just technical questions, chain resilience, environmental stewardship, and global cooperation. So, to help us navigate the complex multidimensional landscape, we are incredibly fortunate to have with the distinguished expert whose career has been dedicated in understanding very fundamental material behavior under extreme conditions, work that is direct application to energy storage, high temperature processing, sustainable resource and utilization. And it's my distinct honor and pleasure to introduce our esteemed speaker, Professor Lukman Mahmud. Professor Mahmud is currently Professor and Associate Dean Industry Academic Interface in the Department of Mechanical Engineering at Somaya Vidya Vihar University, Mumbai, India. He holds a PhD in Material Process Science from prestigious Royal Institute of Technology, KTH, in Stockholm, Sweden, where his thesis focused on thermophysical property of slugs and slug metal interface. He further honed his expertise postdoctoral fellow at the CSIRO in Australia, contributing groundbreaking work on dry slag granulation and waste heat recovery. In short, Professor Mahmud bridges the gap between fundamental material science and real-world industrial application. Today's session, Professor Mahmud will deliver his presentation. Please, Professor Mahmud, time is yours.
Okay. Thank you. Thanks a lot for that very elaborate introduction. I hope all of you can hear me. So can I start off with sharing the slide?
Okay.
Yeah.
Please.
So just let me know if you can see my.
Not yet.
Okay.
Okay.
Yeah.
By slowly, we'll. Okay. Good. I think everybody can see this presentation.
So I'll just minimize. Maybe I'll switch off my camera because that would be saving a bit on the bandwidth.
That's right. That's right. Also, become
Just
clear
to
for
be.
us.
Yeah. Okay. So, good afternoon, everyone. This is Dr. Lukman, and I'm with the Mechanical Engineering Department at KJ Somaya College of Engineering, which is a part of Somaya Vidyavihari University. My talk today is on the materials limit for energy storage. Now, I'll just put my laser pointer options so that that helps in a bit of guiding. Now, when I say energy storage, there are different types of energy storage. I also work on thermal energy storage, which is a different aspect. But here we'll be looking at batteries as the mode for energy storage. So the talk will is a generic one, which will be looking at the supply chain, the chemistry, and the sustainability, and also a peep into the way forward and how do countries like India, Indonesia can move or way forward in this aspect. Because this EVs and any the batteries that is being used, it is going to stay with us for a long time. So my contact details is there, the email, in case anyone of you are interested in writing back, that is there. My outline will be basically I'll have a couple of slides introducing our university, which is sort of a general practice, and then we'll dive into the actual topic where we'll talk about the type of EVs that we have, the EV production, what drives it. Then we'll look at the battery technologies. We'll also look at um, what is a viable technology, or are we really adapting just to satisfy or to move along with the crowd? And for a country like India or Indonesia, what could be the way forward? So Somaya Vidya Vihar is based in Mumbai. I'm sure most of you must have heard about Mumbai in one way or the other. If not, then if you maybe the term Bollywood would actually uh, help you to understand it better. But then in Mumbai, which is the economic capital of India, Somaya Vidya Vihar lies almost in central of the Bombay. So that sea over there is basically where we are located, and that's where located Mumbai is located in terms of uh, the entire country, western coast. Now, if something about the university, we are, as mentioned, central Mumbai located, and it is pretty good in terms of connectivity. We are the first state private university of the state of Maharashtra, and we were set up in 2019. Although, if you see, the college has been there from 1940s onwards. Uh, a campus is around 50-acre campus with around 28 acres dedicated for the university. We have 16 schools. The 16 schools are mentioned over here. So I'm representing the School of Engineering. That's why it's mentioned in bold. We have around 800 faculty, 9,000 students, 197 programs. We have two incubation centers where we look at startups and funding startups, discussing what new trends can be looked at for businesses and stuff like that. We in Mumbai, to have a hostel is a great privilege. We have three of them in the campus, and we have one or two outside the campus. In our second campus, in fact, we have 16 sport facilities. This is a new facility that we have started along with the university, and recently we have hosted the World Squash University Tournament, of which India won the first place. We are also linked with the Association of Indian Universities, and we do try to execute some research projects through which we have the CSIRO uh, certification and also the UGC recognition for that. This is our campus. This is basically where we sit. Currently, I'm sitting in this building, which is these two are the engineering buildings. So we have Aryabhat and Bhaskaracharya, and this is where I'm located. That is the sports complex. That is the management. Then we have the research wing over here, the schools. So we have starting from the schools to the advanced management and engineering colleges we have, and also we have arts and science on this side. A bit more on the engineering. These are the branches that we have. We have 10 BTech programs, 9 MTech programs, and 6 departments which offer PhD. And in mechanical, we have postgraduate courses on energy and CAD/CAM and robotics. And as I was mentioning, we also have a robotics and artificial intelligence, which is offered by the college. Okay, so let's now dive into the topic itself. Again, whatever I'm mentioning are from the statistics taken here. I may try to put things in my perspective, but then the listener is expected to have their own understanding and maybe wade further on this one. Okay, so this is one of the EVs that we're talking about. And since we talked about energy storage, naturally now everyone knows that EV is right now in fashion, especially in the people who are interested in automobiles and the sector itself. This is an all electric vehicle, which means from start to end, it's the battery that drives the vehicle. You have also plugged in EVs, you have hybrid electric vehicles, but all these various formats, definitely use batteries, but in different quantities and sometimes different technologies also. Now, if you look at the vehicle as such, that is given on this end of the spectrum, we start off with something called as active materials. This is basically the anode and cathode black mass that we refer to, which actually helps in storing the energy and delivering it. So if you see, this is what is actually contributing to the entire energy storage. Now, this along with converting the powder to a more moldable form. So where you have the powder being basically added on a foil. This could be an aluminum foil or copper foil, depending on whether it's an anode or cathode you're looking at. And then this foil goes into a cell. Now, cell again, you have different formats. We'll look at that later on. And in this cell, you have the anode cathode, and definitely you have a separator because you cannot have both of them lying next to each other. These cells get scaled up to a module level, then it goes to a battery pack, and then it goes to the vehicle. So this is how your transformation happens. And if you see, the contribution of the active material at the end is very small, but then that is the basic heart of the entire system. And that's what we are trying to look at over. Now, what drives this EV craze? Although I have put some data which is relevant to the Indian scenario, uh, you have a similar trend worldwide. So just look at the trends. You may not dwell on the numbers. So if you look, why is EV sort of fashion is because this environmental awareness. People are now talking about save the climate, bring down the greenhouse gas emissions, bring down the temperature, make things as it was a couple of years back. So that is the driving force. And this electric vehicle, in terms of its operation, sits well in that. By means that it is assumed that you don't have any greenhouse gas emissions with no CO2 emissions. And there are some statistics which talks about that this is what sort of scaling you're going to have from 2005 to 2030. And this is how the market of the EV sales has happened. And this trend is there for all countries. Now, along with this, when I say market, we have a four-wheeler market and we have a two-wheeler market. And in India, and I think also in Indonesia, you have a very significant what you call market for the two-wheelers. People tend to buy more two-wheelers than four-wheelers, naturally because of the price difference. And now two-wheelers are also becoming electric, which means again you will need to have more materials for making batteries, more energy storage options and stuff like that. Okay, so the sales also is assumed to push up to 30%. And just to put things in perspective, this is basically how much an average car BEV costs in India. It's around 14.1 lakhs, which is around 26.46 crore Indonesian rupiah. Now, if I burn down into a particular vehicle and see what you have inside, in terms of the cells, the number of cells, how many things are in parallel, what is the mass, what voltage. So this is one of the statistics that I have taken it from Tata electric vehicle, basically a Tata Punch over here. Uh, Now, if I have this Tata Punch model, which has an EV and a non-EV model, I will have around a 320 kg difference in the weight. Now, this 320 kg difference is predominantly because of the battery pack that you have over there. Okay, and that's what is mentioned over here, to around 220 kg approx. So this for different models you have different weight differences. Now, as you can see, when I'm talking about these 200 kgs of battery weight, it's the black mass is only a small fraction of it. You have steel, you have aluminum, you have nickel, you have all other metals also coming into picture, which contributes to the entire battery, right? And yeah, one significant thing that we want to see for India, this is the latest technology that we're using, LFP, that is lithium iron phosphate. Now, if you look at Indonesia scenario, this is something I've taken over the net. You can see the same trend is there for Indonesia. It is also peaking up. And if you see around 20%, close to 20% is your BEVs and hybrid PHEVs, plug-in hybrid EVs. So you have around 20% of market already is taken up by the EVs. And a significant market is coming for the two-wheelers also. Some companies, like if I remember correctly, Wuling is also coming in a big way in the electric market. But then if you look at the government, the targets and the actual reality, we are still, even in Indonesia, I think it is way lagging behind. The same case is for India. But then if you imagine we are reaching the targets, how much or how much battery material you would be requiring with that aspect. Now, if you look at Indonesia, they're slightly different from India because Indonesia is the world's largest producer for nickel. So you have a very good resource for nickel. Since nickel is available, cobalt also is there in moderate senses. Because nickel and cobalt, if you see, they are pretty much close in the periodic table. So if nickel is there, cobalt is there, and also a bit of copper also. So these are the transition metals, so they tend to be close by. So Indonesia government is also trying to push NMC, which is your nickel, manganese, cobalt format of your EV technology, while in India we are having LFP. Now, just some comparison between these two to add a bit more perspective. Now, if I look at these two technologies, NMC as well as LFP, now if I talk in terms of range, the NMC battery is definitely meant for performance. Performance means in terms of energy delivery, in terms of the uh, yeah, the energy, the power. So that is when NMC takes uh, takes the cherry, or it's the winner. Okay, LFP, it is usually meant for low energy density and shorter range. Okay, so if I'm saying city drives, LFP would be the preferable technology. If I'm talking about a bit of long drives, again, there's a limit to that. NMC would be the preferred one. If I'm looking at cost, naturally, I'm talking about nickel and cobalt, which are extremely costly elements as compared to iron and phosphorus. So LFP scores over there. So if I want to bring down the cost of the vehicle, LFP technologies needs to be adopted. If I look at the safety, LFP again comes into picture because your chemistries for nickel and cobalt are pretty reactive. Charging habits, again, the charging, when I say charging habits, I'm also taking into consideration the thermal runaways, that possibilities of overcharging, overheating, and stuff like that. In that aspect, LFP is always preferred, usually preferred. In terms of number of cycles, or what we call as longevity, LFP again. Fast charging NMC, as I said, uh, you have a high delivery, so range is less. So your fast charging things. So if I want to plug in the vehicle, charge it fast, and then leave, NMC is more preferred. But then because you're doing fast charging, you also degrade the battery. Now, this is something interesting. For cold weather, NMC is preferred, while for hot weather, LFP, because LFP doesn't have that overheating aspect. So, whether it is Indonesia or India, I think both of us sort of come in the hot weather or normal to hot weather sort of climate. So LFP is the technology which is more favored over there. And if I say cold weather, we are talking about countries like northern countries, like let's say China, certain parts of China, Europe, and stuff like that, where you have a relatively cold climate. So NMC is more preferred over there. Naturally, if you look at the environmental aspect and ethical aspect, LFP is preferred, and the reason of LFP being developed as a technology itself is the environment aspect, and that we'll talk about later. If you look what you have inside, it's the cathode that is different. So you have both are layered oxides, which you have. One is olivine, other is NMC layered oxide. Because it's a lithium ion battery, naturally the reason for that lithium ion to be there is it's the lithium that moves between the anode and cathode, causing charging and discharging. The material, the anode and cathode, does not move, does not take part in that. Natural energy density, as mentioned, it's lower on the LFP as compared to NMC, and cycles naturally is on the higher side. These are some of the representation. So what I want you to understand is that if I want to charge, when I say charging means the lithium will go into the anode section where you have graphite, or sometimes in NMC formats you have also graphite silica, carbon and silicon. So graphite being layered structure, the lithium can easily set in inside. And when I say discharging, you have the lithium moving away from the anode and sits inside the cathode. So that's how your charging and discharging happens in both formats. Okay. Now this is something I would say it's based on human nature. The bigger, the better. Nowadays, if you look in the types of or the models that are coming out, there's a good, at least in India, we have seen a good inclination towards the more meatier, bigger SUV or crossover vehicles, and that's what you can see. Within a year, you have a sudden drastic change of people liking to have or preferably buying an SUV against a hatchback or a sedan. Okay, so naturally the SUV is bigger, bulkier, it's more heavy, you need more energy to pull it out, so your battery weight also will increase. So again, there's a demand on that aspect as well. Now some basics. Now I'm not going to dwell too much into the basics because this is meant to be more of an awareness talk. As mentioned, I have a lithium ion battery. I have an aluminum plate or a foil, a copper foil. The copper foil will have graphite on it. The aluminum will have my lithium compound on it, or lithium salt, or sometimes lithium oxide. In between, I have a separator, which is majorly a PVDF, PPE sort of polymer, a separator. And what you see over here, the small dark spots are my lithium. The lithium basically moves in and out through the separator. So once it goes in between, sets in between the graphite hexagonal layers, you basically have charging, and as it gets consumed, you will see that the lithium moves in the reverse direction. Okay, so that's your discharging and charging happening. Okay, different morphologies demand different quantities of material and different formats. So generically what I have is I have an anode which is technically going to be graphite, sometimes graphite and silicon, and nowadays they are trying to develop new materials in this aspect. The cathode is going to be a lithium compound, preferably a lithium layered oxide. The reason for layering is that the lithium has to move from between the layers to the layers of your graphite. Graphite is anyway a layered material. So the lithium moves in and out. Electrolyte is a polymer membrane, and these are some of the different formats that you have. We have cylindrical, prismatic, pouch. For R&D purposes, people tend to use coin formats also. The intention is I should have more active material, which is your battery material, squeezed in the same dimension. So this is basically a couple of rolls of anode, cathode, and electrolyte or material. And when I roll it, I have multiple layers. And these are just different formats. The same thing, if I fold it in this format, this is what I get. In pouch cell, I basically have planes stacked with leads through which I can extract the current or connect it to an external load source. Now, if I want to compare the cell morphologies, naturally, if I want to go for higher energy densities and the cost side, say the lowest cost for the best energy density, cylindrical format is what I would prefer. And most of your vehicles do use cylindrical cells. If you look at laptops also, because there's a limit in the space and there's a good amount of energy requirement over there, cylindrical cells is what you will see when you open up any of your laptop battery side. Most of the time it's the cylindrical cell. However, you do have other two options also. Now, digging deep into the chemistries, now here, rather than talking about the chemistry as such, we'll see the evolution. So if you see from left to right, this is how the cathode chemistry has evolved. Why the cathode chemistry is because the most, the potential drop is more at the cathode side. So people try to bring that down by trying different cathode materials. The same thing is happening in fuel cells also. So the first battery had lithium cobalt oxide. Now, if you see most of the batteries that are in your recycling unit will have lithium cobalt oxide, because nowadays people don't go with this particular format, especially because you have developed higher end NCM, LFPs, and NCAs, that is your nickel, cobalt, alumina sort of batteries. Okay, so as the market share is mentioned over here, the main force, and this is steadily growing, and this is also growing. Okay, and here we have different uses. So you see LFP for safety point of view, the cost point of view, thermal stability. So you have very less thermal runaways and overheating explosions happening. That happens very, very less in LFP technologies, but the same cannot be said in the other two formats. Barring which, it doesn't mean that it's going to explode all the time, but the chances of that event happening is very less in LFP. Now let's burn down a bit more into the entire battery itself, and let's break it down into the metals or the materials that you have in it. Now, if I see the cathode chemistries, now here I am talking about NMC, NCA, and LFP, which is your nickel, manganese, cobalt, nickel, cobalt, alumina, and lithium iron phosphate. Okay, NMC also has different formats, as you can see, 811, 523. So that depends on 80% nickel, 10% manganese, cobalt. So it's basically the ratios that we're talking about. Now, if you look at the total amount of lithium is only 5 kgs. Cobalt, as you can see, I'm avoiding cobalt in LFP, and that is one of the reason that LFP was actually coming into picture. Nickel also is avoided over here. Now, this LFP technology is something that perhaps Indonesia would be adopting with a pinch of salt, because the technology is cost effective. However, it also does not ensure the use of one of your largest resources. Okay, but there's always it's sort of a twin sword thing that you have over there. Manganese also is another element that is in the NMC, because the center is basically a manganese. Graphite, which is one of the single most abundant element that is in a battery. As you can see, compared to lithium, it is at least 10 times more, 10 to 11 times over here, if you can see 6 and 66. Aluminium, this is for the foils and other stuff that you have. It's also there. Copper connectors, interconnectors, all these things are also coming to picture. The copper foils and your anode side is also there, contributing over here. Steel casings for the batteries, okay. And iron over here, it's usually iron is not used, but then LFP has iron, so a major portion of it is basically iron. And this is the reason why this battery is relatively cheaper. But then what I want you to understand is this, although the name says lithium ion battery, lithium is a very small component over here, but it is the most crucial component. Without that, run. Now, if I want to actually look at which battery is which, it sometimes nowadays it's relatively easier, but then at some point of time, if you were to look at it maybe around 5 or 10 years back, it would be difficult. It would have written only lithium polymer battery or lithium battery. This is the only label that was there, not anything really deep into it. There was no labeling like plastics. If you see plastics, you have this one, two, three, four different plastics have different labelings. So in that aspect, you can identify what it is. In this case, it is not there, which means now this will actually create a problem when you talk about or when you want to do recycling, because then you will have to process different technologies at the same time. And that's one of the key challenges that you have in the recycling uh, aspect of these batteries. The same thing put in a more picturesque explanation, which tells you that, okay, in your entire battery pack, you have around 28% is your graphite, 18% is your aluminum, nickel is 15%, your copper is 10%, steel is 10%. You see, if I want to look at lithium over here, yeah, that's lithium, 3.2%, and the lowest is iron. Okay. So if you look at a normal EV battery, now this is not an LFP battery. It could be an NMC battery or LCO battery that is mentioned over here. It's relatively less. Now we talked about what is inside the battery. Just a generic explanation of how you make a battery. Let's say one of these cylindrical cells. So naturally, you will decide which technology you want to use. Accordingly, you have to take some raw materials. The raw materials need to first be heated in a tubular furnace to remove any moisture. Then they are ground to very fine nature using a planetary ball mill. This is majorly to ensure that you have a very high specific surface area and things, the reactions, the reaction rates are on the higher side. Now, when you want to bind it, there are certain critical binders that you have to use, which are pretty much reactive to the atmosphere, and hence you need to do vacuum mixing, because once you have these powders, you need to mix it well so that they form whatever compound. Once this vacuum mixing is done, it's done in a sort of a slurryish mode. They are then electrode coated. Now, although this is done in vacuum mixing, from this part onwards, we are putting it in a glove box. The glove box ensures that the vacuum is done or an inert atmosphere is there. So all these parts will basically be hubbed or housed inside this. So over here, what I do is I make an electrode coat, which means, let's say if I'm going for a cathode material development, I would use the battery grade aluminum on this, and then the mixture will be put on this, and this, if you see, this portion moves horizontally. So it's something like a doctor's blade. You can decide what thickness you have, mostly maybe a micron thickness, and then it moves and it creates that sort of thin layer on top of your aluminum foil. Now to consolidate that, you need hot rolling. So that's my hot rolls, which are, I can heat it, and also I can adjust the distance between these rolls. Then depending on what size, if I want to make pouch cells, I need to cut it into certain dimensions so that sheet cutting options are there. And then after doing this, because although I have done this, I would just want to avoid any sort of secondary moisture that is being captured. If some of my components are, let's say, hygroscopic in nature, I would want to do a vacuum drying over here. And then I may or may not go for an spot welding machine. Now, the spot welding machine is basically, let's say, if you want to make a cylindrical cell, you have these rolls. You need to have sheets of anode, cathode, and electrolyte piled over each other, and you need to roll it. So whenever you try to roll three pieces of paper, you'll see that there's always going to be a slip between these papers, and you end up with one moving faster than the other. So this, what you do over here, you spot weld the starting point so that there is no motion between, relative motion between the sheets, while you roll them up to form a cylindrical uh, battery over here. Okay. Now, couple of other machines are also there. Again, it depends on over here. It's electrode winding, which means that rolling aspect is here. Your grooving machine, so your casing needs a groove sometimes, and then your ending you need to spot weld it and then seal this case. Now, before sealing, what you do over here, these are all hot processes. After making the roll, after making this casing with the material inside, you tend to add a calculated amount of electrolyte. The electrolyte with the separator sheet put together forms the final electrolyte that you are going for. Okay. Now these units, like your cylindrical casing, this is meant for coin cells. And after you make all these things in the glove box, you can test for your charging, discharging profiles and everything using a battery tester. So this is how you do it in a research-based lab. Even the mass production also has um, automated streamlines of these things put in or it's housed in clean rooms. Now, we have talked about the components that your battery has, and if you see, all these components are actually being reflected in something called as critical minerals. And this is something that most of the countries, perhaps except China, who are talking about, because this will decide uh, how your country grows in the future, especially the material that goes in batteries, the material that goes in permanent magnets. So, because permanent magnets looks as the medical side of things, and batteries looks at most of the operating power for automotive, let's say laptops, mobiles, everything. It's a real necessity nowadays. So, if you look, lithium, beryllium, potassium, strontium, titanium, vanadium, cobalt, nickel, copper, all these things are critical materials. Now, some of you would be surprised, why is copper and why is, let's say, aluminum also, this also is going to come soon as a critical material, because the amount of usage that is happening right now, especially in copper and aluminum, they have multiple uses across streams. At some point in time, you won't have enough raw material to go for it. So copper and aluminum, currently they have their own recycling streamlines. So you have a tertiary source for that. But still, depending on your use, it can happen that aluminum at some point of time, maybe in the next 5 years, will go extinct. Extinct in the sense, it will be called as a critical mineral, and you will have to look at it in that way. Okay, so now what we're going to look at is, we have looked at these elements like lithium, cobalt, nickel, graphite. These are the components of your batteries. We'll just look at how are these things obtained, which what we say, these all things put together makes a battery. And battery for us is like, is environment friendly. You're trying to replace internal combustion engines with battery vehicles so that you don't want any CO emissions. What you're going to get out is only pure electricity and stuff like that. So let's see. I'll just skip this one because we have already talked a bit on it. My first metal is copper. Copper for the anode. On copper, you have the graphite being coated, so the copper foil comes first. In India, we have a decent number of mines, although we may not be in the top producing countries. Indonesia is there, so you can see that Indonesia has good amount of copper, as I mentioned, because nickel, copper, and cobalt are pretty close in the periodic table. The availability is there. But in both countries, we do have. Whether we have enough for the sustaining needs in the future is a big question. Definitely, India does not have it. Sorry. Now, in terms of production and consumption, I will just talk in terms of India. The same thing is could be similar with Indonesia also. Now, before we look at the consumption and production over here, this is where it is being used: electrical, telecoms, transport, building construction, consumer durables, defense. So these all is where copper is being used, and batteries also come in this picture. In India, uh, we tend to import a decent amount of copper, as you can see over here. Now, how is copper produced? These are my different ores of copper. Now, just to give you one perspective, when I say ore, let's say iron and steel making, when I say iron ore, it is iron oxide. Now, if I take a natural rock, I would have some amount of iron oxide there, maybe 5%, 10%. But then what is the workable limit for iron oxide if I'm talking about iron and steel? Usually, if it's a really good ore, I would say anything above 62 is probably one of the best ores you can get. Nowadays, people are working with 58% iron oxide, which means the remaining 42% is gang, and you don't want it. And a steel plant basically processes roughly 50%, or let's say 40% of unwanted material. So this unwanted material is heated to 1500, 1600 degrees and it's processed. So you can assume how much energy is actually going over there without any use. You cannot do anything about it. It is going to be there. The same thing if you look at copper, it's way, way, way worse, because a good copper ore typically has only 0.5 to 2% copper, which means if you are doing something like steel, you're processing 98% unwanted material. Technically, you don't do it in the same way. So here we have another process which we call as beneficiation. So what we do over there, this 2% copper, or let's say 1.8% copper that we have, is being enriched. So we have different techniques. For example, I can use something called as a froth flotation technique, where I crush this ore, very fine powders. I add a surfactant. The surfactant actually links up with the copper ore element material, and it takes it up. So I'll be skimming this just like the froth on top of this entire large container, and that is then taken further on. So with this process, I can move from 2% copper to roughly 50-55% copper, which makes things more better to then process it using other techniques. Okay, so unlike steel, copper has a beneficiation process in between, majorly because the availability is very, very less. I just put a diagram over here. So this is how it is being mined, or what we call as extraction. I can have open pit mining, underground mining, or I can have leaching. Leaching means when it is available in the liquid form. For the underground and the open pit, I usually crush it, grind it into fines. I do froth flotation, as I mentioned over here. So the froth is where I'll have the enriched copper. This is then skimmed, and then I can either use a traditional roasting smelting process. Now here I'm saying smelting, it means melting along with chemical reactions. Okay, I can form slag and matte. Sometimes I use flash technique, which is a different technique over here. And then from here, the copper matte, which is again enriched with good amount of copper in it, is then I use electrolysis to further purify the copper and obtain it in different forms. I have another route which looks at the liquid. Okay, so I can have extraction processes and electrotwinning to give me some final parts. Now, in all these processes, I am heating, holding, waiting, pouring, all these processes done at high temperature. If you look at melting point of copper, it is 1083 degrees Celsius, and most of the furnaces in copper, they run at temperatures around 1350 to 1400 degrees Celsius. So the average industry emissions, if you look at it, is around 4.1 tons of copper dioxide per ton of copper. So this is the amount of CO2 that is being generated if I want to process 1 ton. Okay, and this is the amount of energy if I want to make a copper cathode, which is my final product, 24 to 37 gigajoules. Not only copper, not only electricity, water is also required over here, especially because when you have a leaching process, water is also required, and it's a water extensive process. I need around 170 tons of water per ton of copper produced. So if you see production of copper, you have this. It's not a green process at all. Let's come to nickel. Now, this is something that Indonesia is the largest producer. Again, where is nickel being used? Predominantly stainless steel. India does not have any significant source of nickel, of that matter of fact, but then maybe a few random ore sections over here. But then our major nickel is coming from recycling or extraction from the existing stainless steel itself. Now, if you see over here, batteries have contributing to 8% of this one. The largest producer, as I mentioned, it's Indonesia. So nickel is not a problem for Indonesia, but a big problem for India. I should add over there. This is what India has, very, very less. And sorry, recently, Vedanta became the only producer for nickel in India. Very small quantities. Sorry. Now, just like copper, nickel also has a similar route. We start off with the raw material, which is again 1 to 3% nickel. The ore only has that much. So again, I have to do what is called as beneficiation. That is increasing the concentration of nickel compound in it. And I can do smelting, or I can do extraction, electrotwinning. This is the same process that is followed, a similar process followed. Like how you process copper, you do it for nickel. If I look at the equivalent, CO2 equivalent is around 13 to 45 tons of CO2 equivalent per ton of nickel is required to produce nickel. Okay, now we are going to talk about a material which, as I mentioned, is perhaps the largest in terms of the quantity that is available in a battery, which is graphite. Now, graphite, India has a few sources. Pardon, I'll just take a break for drinking water. Yeah, so what I was saying is graphite, if you see, it is used in the anode, and being a natural laid material, not all types of graphite can be used in batteries. So the natural graphite is one thing. Then we have something called a synthetic graphite. Synthetic means I'm taking a carbon precursor and then converting to graphite, which naturally means that I have to add more heat and more materials to it to modify its structure. Now, why graphite? High electrical conductivity, high thermal conductivity, high temperature resistance. You have graphite resistance furnaces also. Cost is relatively low. Naturally, it doesn't look very good, so people don't pay for it. But then now, since battery has become something like gold, the graphite also has gone up. Energy density is high, and it has a relatively long cycle life as long as you treat it in the proper way. Where it is being used, your redox batteries, fuel cells, lithium ion batteries, all, if you name all the new technologies, carbon is there. And one thing I would add over here, later on, technology is going to be either carbon engineering or hydrogen engineering. So these are the two things. If you look at any of your new processes, it's either carbon, you handle carbon, or you handle hydrogen. This is how it is going to come out. In terms of the natural resources, natural carbon, natural graphite resources, China is the number one player. Indonesia, it's not there. India has some of it, not as much as the requirement is there. But then, if you look at China, just like lithium, which we'll talk about later, China has the largest resource and it also is the major player in the processing. So, which means China is right now dominating both markets, the production as well as the fabrication, which is technically a very scary situation. Yeah, some numbers, if you look at it, natural graphite, I basically expel around 1 to 2 kg of CO2 per kg of graphite produced. If you look at the synthetic graphite, which means I'm talking about a hydrocarbon or a carbon precursor, I need around 4.9 kgs of carbon dioxide, which is expelled per kg of graphite. Majorly because when I say hydrocarbon, I usually have a good amount of sulfur associated with it. Okay. Different routes, synthetic graphite. So these are some of the, if I want to convert a natural graphite or a synthetic graphite to a battery grade graphite, these are the things that I need to do. I need to have a process called periodization, purification, then coating, and then it is fit for battery grade. So just having graphite is also not enough. I really do need to have some post processing to the graphite to make it usable for batteries. Yeah, and this is what I've been telling. If you look at synthetic graphite production and battery anode material production, which are two different things, both China is dominating around 80% to 85% of the market. So next time you want to have a battery, China will dominate. That they can dictate the prices. Okay, so I'll skip this one because it's pretty similar. Uh, I just put this three different routes just for understanding the energy requirements over here. So the audience can just go through it randomly. So if I have natural graphite, your graphite mining, you get your gangue, which has around 50 to 90% carbon. Then you have mechanical separation. You need, sorry, you need to crush it to make it more reactive. Sorry about that. Yeah. So you need to separate the graphite powder by a flotation process. Then you have drying, shipping, milling, downstream process. So you do have energy coming into the picture. You do have other material coming into picture, like your downstream processing requires hydrofluoric acid treatment. And then you get your battery graphite, which is around 99.9%. So from 50% to 99.9. If we look at synthetic graphite, so I can start off with a low sulfur petroleum material, which is a hydrocarbon. Then I go for catalytic cracking distillation, which means technology driven. Then if you see over here, I need to heat it at 1500 degrees. I need to convert it to the graphite sort of structure, which is your layered hexagonal layers. I need to go up to 3000 degrees Celsius. Okay, and that too for prolonged times, 7 to 21 days. So you can imagine how much energy I need for it. There is another route where people are looking at biocarbon. Uh, if you have biocarbon, again, biocarbon is obtained from a biosource, which is basically pyrolyzed, and then you enrich it to 80%, or you can also maybe rip off the lignin from your biomaterial or biomass residue. So you can have a lignin coming into picture, which again you have a graphitization process, which is a lower temperature. That's a good thing about this. You don't need to go for 2000 degrees, approximately 1200 degrees. and then you can do some downstream processing to get your battery grade graphite. So people are looking at this aspect. People are also looking at other aspects, which we'll talk after the presentation. But then what I want to see on this slide is manufacturing of carbon or battery grade carbon is extremely energy intensive. Naturally, more energy, more CO2 generation, because in both countries like India and Indonesia, our prime contribution to the energy mix is through thermal power plants, which is coal or coke based. Next element is aluminium. Aluminium, if you see, is pretty much used material. If you see, Indonesia has 3%, India has 2%, pretty close to each other in terms of aluminium or what say bauxite resources. But if you look at the production, India tends to go a bit ahead as compared to other countries. The main thing is this 6% is also contributed by the recycling of aluminum. So we have a may not be a very sophisticated way of recycling, but we have a good amount of recycling, smaller recycling plants which recycle the used aluminum. Most of the countries do have it. Now, if you look at the processing of uh, uh, the aluminum ore, which is your bauxite, I need 6 to 7 tons of ore to produce 1 ton of aluminum. Okay, so you can imagine how much material is wasted. Two, what sort of process you need to do the mining? You need to make the alumina first, then you need to smelt it. Smelt it again, it is majorly done by electrolysis. In Australia, they used to have a lot of aluminum smelters, especially using your Holt Herald process. But then, because of the electricity cost, a lot of them have been shut down. So this is heavily dependent on the grid electricity. And as you know, electricity in both countries are carbon driven. So again, you have a contribution of CO2 over there. So again, I would like to say there's a good amount of CO2 generation to make aluminum. Some numbers in terms of emissions. This is basically million tons of CO2 is being produced. For mining, it's 3 million tons, refining 171, smelting it's 855. So this much amount of CO2 is generated. Finally, we come to the most dashing material, whose name is basically being used for the battery itself, that's lithium. The, the, the element which is the least in number, but the most important. Now, if you look at the availability of lithium, it's not a pretty much available metal. You do have a good amount of it in Australia and a good amount of it in Latin America, especially in Chile, Argentina, Bolivia, Ecuador, those sections. But then the format that you have in both are different. In Australia, you have the open pit mines, so it's majorly occurring as a proper ore. But then the ones that you have, the lithium availability in Latin America is majorly in terms of brine solution. So the processing are two different things. Now here is a fun fact. I wouldn't say fun, but then it's a sort of an irony. Australia has been sending its ores to China, where it is being processed. So the Australian ore goes to China for processing, and the Latin America call the Chinese people to come to process their ores over here, because this thing cannot be traveling. This one can. So if you look, the China involvement in lithium is also significant, because the technology requirement for processing both the uh, rock as well as the brine is with China. So although other countries do have good amount of sources, it is China who does the processing, and this is something that other nations should actually think about. If you have something of yours, you should actually uh, take it to the next level by processing it. Again, some numbers in terms of the CO2, the amount of water, and the amount of land that is being used. If I look at hard rock, which is available in Australia, I have 15,000 kgs of CO2 being um, liberated when I'm processing 1 ton of lithium, 170 meter cube of water, and the land requirement is 464 meter square, which is less. But then if you look at the brine solution, sort of the Latin American version of the ore that you have, uh, the amount of CO2 comes down, but the water requirement goes up. So either you have a CO2 or you have water being used. And the land requirement is also significant. It's way larger. The last one, now I kept this for the last, is because at one point of time it was the most costly element in a battery, and still now it is one of the costliest element, um, and one of the most controversial, cobalt. If you see the uh, production of uh, cobalt, 72% is with Congo. Indonesia has 3%, which is also a great number. But then Congo has 72%, and Congo being a underdeveloped nation, the Western and the European and many countries tried to exploit uh, to get the cobalt material for making their lithium cobalt oxide batteries. And that's one of the reasons why people started moving away from that after a lot of environment awareness and exploitation happening. Because with cobalt, what happens, it's a pretty carcinogenic material. It creates skin itching. It's not good for the eyes, not good for your respiration system, and it is carcinogenic. Okay, so because of this, that LCO technology has moved on to LFP. So you can see that LFP basically avoids any amount of, absolutely zero amount of cobalt is required. And that's how the technology has emerged. Okay, so now coming to the way forward, as you can understand from the talk itself, although the battery seems to be a very beautiful way, it looks great when you have it on the car. Although you have certain skepticism that how long can you drive it, and you have a concern that where is the next charging station, and that's a thing that can be developed later on. But it is not as we see it. There's a good amount of CO2 generation, good amount of water being used. I mean, it's not uh, environment friendly at all in that aspect. If you see from the start to the grave, the way forward and the way forward, especially for countries where these sort of critical minerals are not available, and in order to again break the over dependency on certain nations, the way forward is only recycling. Whatever we have, you try to recycle it and put it back to the system. Okay, and in that aspect, you can see the battery market. Now, this is combination of all formats and all requirements. It's boosting up. It's in 2030, in 2050, it will go way beyond this. So, what can you do? Recycling. That's the key thing. Again, as I said, it's not as simple as plastic where you can identify which technology you have. But then there are certain methods through which you can actually think about recycling this. Okay. This is some of the prices just to put an economic sense on this. As I mentioned, cobalt is one of the most costly material. Went up to 55,000. Now it has come down because the usage is slowly dropped. People are moving away from the cobalt usage. But then if you see, lithium is anyways going up steadily. Now, if I look at the life cycle of a LIB, I can have it from the first use till it goes to recycling. I can either go for after the usage, I can disassemble it. I can replace certain batteries which are not performing. This happens usually when you have a EV with you. During the maintenance, they will check for each battery pack and see which is not performing. Only that battery cell is being replaced, and then it continues. Then you keep on using the EVs. The non-performing battery will then be refurbished and be used later on, or it can go to recycling. and that's the second stream. Okay, so you have a repurposing, which means the non-performing cells can be looked at. What is the problem? Is it a sealing problem, or is it like a coating problem? All those things can be done. Now once it is completely dead and basically your voltage is way below than what you require, just like how you see in your cell phones, after maybe 3 or 4 years, whatever application used to work earlier on your mobile phone doesn't work anymore. So that's the time when you actually have to take it out, and then you have to classify it according to materials, input materials that you have in your battery, and then think about pre-treatment before recycling. What are the different options you have for recycling? I have what is called as pyrometallurgical options, which means pyro means heat. So I'm heating the material, I'm decomposing it. Basically, I'm reducing the material. Say, let's say if I have lithium cobalt oxide, I will rip off the oxygen, try to get a lithium cobalt mix, or I'll have a material which can be selectively dissolved in an acid or a base, depending, and that's where your hydrometallurgy comes into picture. So this is a low temperature one, this is a high temperature one. Naturally this has its own challenges. It means I'm talking about adding energy to the system, and over here I'll have to think about what do I do with the acids and bases that I use. I have another third option, which is direct recycling, and here I try to add lithium to it, re-lithiation process. It's not all things can be going through this route, so there's a limit to that one. And finally, what I want from this is basically I would prefer to extract, let's say, a lithium precursor. Getting lithium metal as such may not be the viable solution, but if I can get a lithium carbonate sort of solution, which can be used as an input for making new batteries, that is good enough. And also I save that energy of ripping off the carbonate from the system. So I want the aim of this recovery process is to get precursors of lithium, let's say cobalt for the matter of fact, manganese, um let's say, and other materials like copper, aluminum. Anyways, it's a different technique. Right now we are looking at lithium, cobalt, manganese, three of the major ones. Yeah, this is again what I mentioned about, so I'll sort of skip this slide. Yeah, one of the methods that you can use over here is once you have the batteries, the first thing, if I want to see whether it is really there's a requirement of uh, mm, let's say recycling, is I'll first charge it. I'll charge it, and then I'll, using a multimeter, I can actually look at what is the voltage. Usually your cells, single cell will have around 4.6 or 3.7 volts. Accordingly, if you are getting, let's say, less than a volt or maybe just slightly above 1 volt, it means that the battery is not worth. So then what you do is you need to discharge the battery before you do anything to it. Okay, so first I check the battery is uh, a good battery or not so good battery. Then I need to discharge it. There are different ways of discharging. I can either submerge it in a salt solution, or I can do a short circuiting. Submerging salt solution is a slow process, but it's a relatively safe process. The other case, it's a bit. Sometimes it's your battery can explode in that matter of fact. So once I discharge this, the next thing is I need to mechanically separate it, which means separating, opening up the casing, separating the plastics, the metals, the powders, the active materials. So that's what we do over here. Uh, I have another option where I can take the foils itself, the aluminum and the copper foil, and then I can separate the materials. I can do a calcination by means of which I uh, dry off the material and then sort of scrape it and separate the foil. Or I can dissolve the material in a solvent, and then the solvent is then retreated to extract back the material. So here also I can, in this case, I'll be dissolving the foil also sometimes. Okay, some of the lithium ion battery recycling plants in India. This is just to put a perspective to this concept of recycling. We do have a number of startups that have come. I think Indonesia has also a good number of startups and new companies that have come into the picture, especially looking at this as a business. Okay. Now, just to add a bit of flavor, what we have done in KJC, there's a couple of slides, and then we'll wind up the presentation. We also have looked at some of the battery materials, spent batteries. Now, if you see over here, we have tried out with different chemistries over here. So we basically discharge the batteries, and that's you can see the discharging process. Slowly, you'll see the bubble coming up, and the moment your bubble stops, that's it. After that, we also tried short circuiting it. So, and after opening the batteries, this is we have opened up some of these prismatic ones, as you can see over here, and we separated the copper foils and the aluminum foils. The black mass was then mixed with hydrogen peroxide in 1 liter of sulfuric acid and heated at 80 degrees for an hour. And then we did vacuum distillation, through which we got this sort of a pinkish salt. Okay, so this is the expected reaction that we're looking. We are expecting that pinkish salt to be manganese dioxide. Parallel, we also tried to do pyrometallurgy over here for another batch. So this is the tube furnace, which can be heated under inert conditions, which can go up to 1200 degrees Celsius. These are some of the what do you call the calibration curves that we go. We need to identify the uniform temperature zone where I need to put the samples. So this is basically that activity. So we put the black mass, we weighed the amount of black mass in a aluminum crucible. We put it, a boat, and then we put it inside the furnace. We did match, which is basically similar to an XRD analysis. We found that we have around MnO2 around 65.4 for this pink salt that we obtained, and 33% is your lithium salt. So the next step is to try to separate these two together. For the pyrometallurgy route, we heated it up to around 800 degrees. So we still have a bit of the graphite there, and we have manganese oxide, which is around 28%. A bit of cobalt was also seen, which is around 9%. As I mentioned, this is a pretty old work that we have done. Just I put it for perspective. Of late, what we have done is we have tried to separate, identify batteries of the same technologies, and then look at it, your XRDs before and after the processes, your initial phases. The variables were also measured: what temperature, what holding time. We did some thermogravimetric studies. We are also recently we could actually able to extract cobalt metal as such. Although the cobalt purity we are yet to determine, but then the powder is pretty magnetic, which is a typical nature of cobalt. So that we have achieved that level. Okay, so with that I'll stop over here. Just to wind up my presentation, EVs are going to be there whether you like it or not. We have to slowly adapt to this technology. Now, when I say EVs, I'm concerning about the batteries. So whether you use an EV or not, you will anyways going to be using a mobile phone, laptop. So all these already have lithium-ion batteries. So this is going to be there. Um, we do need a lot of critical materials or critical minerals for this, and we definitely need to have a parallel source for these materials, especially for countries where some of these materials are not available. Like for India, a major of it is not available, and for Indonesia, I think graphite and lithium would be a matter of concern. The other materials are more or less there. So, as I mentioned, recovery is the only way forward, and we should perhaps join hands in trying to look at how do we smartly recover materials over from these sort of batteries. So, with that, I would like to thank uh, you guys for the patient listening. If you have any questions, I'll take it from here. Thank you.
Okay, thank you also.
Yeah.
Professor Mahmoud, thank you very much. I think very, very deep, very deep. You can stop your presentation.
I'll stop the sharing.
Your
Yes.
share.
Sure.
I said,
Yeah.
okay. So I think it's very nice, very deep, very complete. I mean, we can understand from from uh, from the beginning how to make battery, and then until finish in your laboratory.
Yes.
Say so. I give question to anybody in the room said would like to ask something, everything about battery. Okay, please, if somebody else would like to ask to Professor Mahmoud, can directly you can speak or reach your hand. Actually, Professor Mahmoud,
Yeah.
Battery is new for us. Some of my
Sure.
friends also doing research about battery. No, not battery, about material, not battery, about
Okay.
material, not battery.
Okay.
So it is new for us how
Okay.
to research indeed on battery, and you can speak from generals until how to make the battery. It's very nice actually.
Mm-hmm.
Also, I
Thank you.
become interest because usually I just know LFP and NMC.
Mm-hmm.
I make electric. 3 years ago, I make in our laboratory electrical vehicle using uh, lithium ion,
Okay.
but
Let them in. Yeah.
lithium ion battery. Uh, Not live PO4, live PO4, yeah. Also
Mm-hmm.
better, but now I become really understand how NMC, LFP, or lithium ion, which one is better. Of
Yeah.
course, depend on the new technology will reach for the battery. So anybody will ask something? Ini ada dari, oh sorry, apakah mungkin penggabungan dua buah jenis lithium 4 dan lithium ion untuk Professor Mahmud, there is a question is, it is
Mm-hmm.
possible to hybrid to mix live PO4 and lithium ion?
To mix and make a battery, to be very frank, I have not come across any research in that aspect because they are two different technologies.
I see.
Lithium LFP and lithium ion are slightly, your anode could be the same. So,
I
what
see.
matters is the cathode. The problem is the moment if you put a mix in the cathode, because although if you're talking about mixing these batteries together, your anode and perhaps your electrolyte would be majorly similar. What changes you are doing is only in the cathode. Now, cathode is such kind of a material is that if you mix materials, if you use mixed materials, you will have a voltage drop over there, which your overall voltage may come down. So that's why people, I mean, if you see, there's a huge amount of research that has been done in the cathode side and not much on the anode side. The research on the cathode side is majorly trying to improve on the voltage. That was, we started off with like 3.7. Now we have batteries which can go for 4.3, 4.8 volts also.
Okay. The question in the chat room, You can see.
Is it possible to combine two different types of batteries?
That is,
Um, when
you,
you
you,
say,
you, you already answer, right? You already answer.
I mean, there's a another trick to it. Like, is it combining batteries together, or like I say, in one vehicle, I use one type of battery for certain application and other battery source for another application? That is possible, if that is what the question was.
I see. So, because Mr. Dr. Jerniko asked me because
Mm-hmm.
he also play on battery because
Okay.
lithium ion and lithium, but there is a, I mean, different different technology and different advantages.
Yes.
Different. So
Yes.
in
It depends on your use, actually. What do you
oh,
want
I
it
see.
for? Accordingly, again, it's a battery selection process. Just like you have different options,
Okay,
depending on what you want, where you're going to use it. All these will decide which battery is the best for you. You may also sometimes have
I
to look
see.
at long term. Economics is going to be one other thing that you need to look at.
Oke, jadi saya, ya, I see. Thank you, Profesor Mahmud. Saya tidak teman sendiri saya yang artikan ya. Nanti saya salah translate lagi.
Okay.
Kalau ngomong-ngomong biasa masih bisa, ini agak agak sedikit itu ya. So sorry, I just translate to my colleagues that
Sure.
uh, they know, but I mean, they can catch uh, what did you say? Okay,
Okay.
anybody can ask another person because cobalt in Congo. So it now commonly speaking, uh, Professor Mahmoud,
Mm-hmm.
in electric vehicle become expensive and expensive, but cobalt remind the people in the Congo become poor and poor. It is our concentration because we afraid also in Indonesia like that. So
Yes.
so
I think,
we have to
mm,
take care of the environment.
exactly. The thing is that it was basically exploitation. I mean, if there was a proper system in place, Congo could have made a lot of profit on it.
I see.
But then there's a lot of other things that, as you can, the pictures basically tell you how it
Okay.
is.
I see. I see.
Otherwise,
Uh,
it is one of the most powerful materials, because if you add cobalt, your performance goes up. And that's
I
why if
see.
you see lithium cobalt oxide, the performance, or even if you see NCM, which has a bit of cobalt in it, your performance is better. Number of cycles may not be that great, but then if you want high energy applications, you
I
need to
see.
have a bit of cobalt.
Okay. Also, Professor Mutia, would you like to give any comment, question, something? Professor Mutia belong to physics laboratory.
Okay.
Professor Mahmud. No, no question from.
Okay, maybe I have a little
Sorry,
question,
Prof.
Parafik.
Saya tidak lihat.
Okay,
Okay.
Mana ini?
yeah, yeah.
Aduh.
Prof. Lukman, actually,
Yes.
I already mentioned before that my research background was now, yeah, until now, it's still based on zinc oxide for
Mm-hmm.
every kind of application,
Mm-hmm.
especially for optoelectronic, actually. Even though recently also my work focus on how to make a clean water contaminant, yeah,
Mm-hmm.
especially for the photocatalyst application. And in another side, I also have a research collaboration with my friend
Okay.
uh, from Chengdu University, and we already have some two publication, and then last publication on 2025, we work on uh, sodium-based batteries. I think
Yes.
sodium-based batteries has some advantages. One of the advantages is comparing with lithium, quite cheap, even though there is some uh, drawback because sodium-based batteries usually they have some dendrite in the surface of sodium. So that's why our research that published last year is how to overcome the dendrite which is appear in the surface of sodium. So my question is, what do you think about the lithium-based batteries for future application? Because I think that we also should take into account the price and the lackness of lithium comparing with other. Yeah, this is first question from me, and the second question, perhaps you can open to have a collaboration with us, especially to guide our students, yeah, because as I know here, perhaps some of the students from engineering and from science may be interested to learn and to do simple thing about the battery-based research. Okay, perhaps we
Oh,
can start whether in Faculty of Natural Sciences or Faculty of Engineering. Yeah, this is, I think, a good opportunity for us to have international collaboration. I think enough from me.
sure.
Thank you.
Yeah, coming to your first question, actually, I deliberately didn't talk much on sodium ion batteries, although the talk was leading towards that aspect. Sodium, as you know, common salt available everywhere. Although there are certain, again, some of those additives that you need to add to make it as a cathode or anode are more costly than the actual cathode materials. And they, again, you do need that high-end equipment like a glove box and things like that, especially because of the binders and stuff like that. But if you look at the sodium ion, there are two aspects. One, on the cathode side, you use sodium, which is naturally available. On the anode side, you don't need to go to graphite. You can use hard carbon, and hard carbon can be made using natural biomass residues pretty easily. Within 1000 degrees, you can get hard carbon of a similar grade. So from 2000 or 3000 degrees for making what do you call battery grade graphite, you bring the temperature down of your anode side 2000 degrees using hard carbon, which is a different format of carbon itself. And on this side, your sodium is there. The only difference is when you put these two together, the voltage delivery is not as great as lithium ion. So sodium ion is good for two-wheelers. So you will see soon plenty of two-wheelers coming into the market. In fact, now itself, I think recently China has they're also pioneering on that. Recently, I think only 2 days back, I've seen the big dumper trucks, these mining trucks being run entirely on sodium ion batteries, EV. It's a even dumping truck, which is used for mining,
Yeah.
that is entirely on sodium ion batteries. Sodium ion battery is good for stationary applications and also for two-wheelers. Four-wheelers, we'll have to wait and watch. Technology will slowly reach over there. So again, there's a big question on lithium's future. It is changing. And answer to question number two, I'm always open. Please do reach out.
Yeah.
So collaboration is definitely possible.
Yeah, thank you very much. Because as I saw in your presentation, actually your method is quite simple,
Yes.
and probably we can realize here, and then we can send to your university to get a measurement, right?
Mhm.
And perhaps
Mhm.
we can start by, for example, if you are maybe agree that perhaps we can start to have a joint publication, maybe, Prof. Lukman.
Sure, why not?
Yeah, and then I will bring you maybe to also to my friend in China, and maybe in the future we will have big collaboration in this area.
Definitely,
I think that's good.
that would be great.
Okay,
So
thank
any
you,
other questions?
Prof. Lukman. Maybe I will give back to Pak Raffi
Okay,
as
okay,
moderator. Please,
sure,
Pak
sure.
Raffi.
Ya, terima kasih, Prof.
Yeah.
Thank you. So, if nobody else, because actually, Professor Lukman, your topics not so easy for us.
Okay.
I
Now I
mean,
try to make it more general enough. Sorry, I
I
went
see.
a bit
I
too
see.
detailed
Also,
in certain places.
but anyway, I mean, for me, also all of my friends can catch detail
Okay.
from beginning until fabrication. So now we understand, but we can start, I mean, in our laboratory to make
Yeah.
electrical vehicle battery.
Yeah.
Mm.
Of course, we maybe we start from our telephone, our
Hmm.
mobile phone is be better. So for closing, I mean,
Maybe we should have taking picture first, Pak Raffi, before we ended our meeting.
okay,
I see a hand raised, I guess.
okay.
Oh, still
Mutia.
someone high. Okay, Bu Mutia, already raise hand. Please, Bu Mutia.
Good afternoon, everybody, and thank you, Prof. Rukman, for being with us this afternoon. Thank you, Prof. Iwan, also for the opportunity. So
Okay.
I would like to follow up. Is it possible to have some follow-up collaboration? For example, is it possible if our students come to your university to have a research together and you become the supervisor or external examiner? Thank you, Prof.
Sure.
Yeah.
That would be possible, definitely. So you'll be in touch. I think Satyendra also will be pretty keen in taking this forward. Yeah.
Okay, very
Nice in you.
So thank you, Professor Mutia. Because Professor Mutia also sometimes when we go to Mumbai.
Yes, I met her. We have met.
Okay,
We have met.
you already met her, yeah?
Yes.
Yeah, okay, that's
Okay.
great.
Okay, we take.
Okay, perhaps next time, Pak Raffi, we will invite Prof. Lukman to your faculty, maybe in Faculty of Engineering.
I see.
My
Yeah.
pleasure.
Prof, itu saya yang komando-komando untuk foto saya tidak terlalu paham. Jadi
Okay.
siapa yang dari LPPM siapa ya? Rido?
Ya, oke,
Dari
Mbak
Rida.
Atia.
Rida foto.
Perhaps Mbak Atia minta supaya Mbak Atianya di depan saya nih. Supaya open cam dulu untuk taking foto bersama sebelum kita akhiri. Prof. Lukman, I
Yes.
think there is no more question to you, and perhaps we can end up our meeting now. Before we end up, perhaps we can
Sure.
taking photo together. Please open all your camera, especially for all the participant. Ya.
Saya
Oke,
bisa
silakan
komando.
Mbak Atia.
Yeah, so
Yeah,
please do send me a copy of it.
Yeah, yeah. You can send me by email also. Okay. Then I also will send my paper that already published last year. Perhaps in the future we can have some joint publication together.
Oke, silakan Mbak Mutia. Mbak Atia, sorry.
Okay. 1, 2, 3. Is it 2? 1, 2, 3. Okay, thank you.
Okay, thank you very much to
Thank you,
Thanks
Prof.
a lot.
Lukman. Nice
Yeah.
to meet
Thank
you.
you.
Oh,
Bye-bye.
no. Hello.
Ya, halo. Silakan, Pak Rafiq.
Profesor Lukman ada di
Udah live.
ya, udahlah. Sudah siapkan kata penutupan.
Ya, mungkin ditutup aja sama Pak Rafiq. Please.
Sudah sama Prof saja. Tadi ya sudah mengarang saya Prof. Sudah mengarang susun yang rapi atas nama RTP dan seterusnya lah ya. Oke, terima kasih banyak ya, itu aja.
Ya, oke, baik Bapak Ibu, terima kasih atas kehadirannya secara daring. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Terima kasih
Waalaikumsalam.
Bapak Ibu semua.
Kehadiran secara Assalamualaikum
Ya,
warahmatullahi wabarakatuh. Tapi kalau di ada main sama Caca.
Naila sama Caca. Oh.
Main sama Caca. Semuanya lupa. Ini kalau tidak oke, akhirnya